Okay. What the heck is that? Okay, we left off sketching rational functions, right? And they were long and tedious, right? And I gave you a homework assignment to try, just to get you working with those again. And I've been asked to go over that problem, which I will do if I have time at the end of class. All right, I'm not going to do it right now, so hopefully we'll have some time at the end. If you have it, turn it in now, because I will not accept it later. I won't accept it after class. Anybody else? Forgot to plug in my laptop. All right, so this is what we left off on. We were trying to graph these, right? And I did the first one, right? Yes, I had not done the second one. So that's what I'm going to start with today. And the function is, well, we're going to see. Let's go through the steps. All right, so there's the rational function. And if you go back and look at the steps, then in one of the steps, which was it? Step F, you could have case 1, case 2, and case 3. And I had given you an example of case 1. And so what I'm going to try and do now is give you an example of case 2, and then the next example will be case 3. That way you've seen one of each type. So we're going to first make sure that it's a rational function. So I'm going through the actual process. Step A, is this a rational function? Yes, because it's a polynomial divided by a polynomial. The next step is to completely factor out the top and bottom. Yes? We're going to see. When we get to step F, we'll look at it. Okay? Step B is to completely factor out the numerator and denominator. So the numerator, what can I do to factor the numerator? Or can I? Factor an x out. So a GCF, greatest common factor, is an x. I'm left with x minus 4. And then on the bottom, what can I factor out? A 2x. And what will I be left with? X minus 8. Right? Everyone good with that? All right, so now we move on to step C. Step C says, look for common factors. If you have them, cancel them out, but remember you're going to have a hole wherever that common factor is. So, do we have any common factors? No. You sure? There's not something we can cancel, top and bottom? The x, right? This right here? X over x. That's a common factor. So you can cancel them out, right? What did you say? That's right. So now what we do is we say, okay, we have a common factor, right? When we cancel it out, we're left with x minus 4 on top. On the bottom, we're left with 2, and then x minus 8. But we have to remember that we're going to have a hole wherever that common factor is equal to 0. So I'm going to have a hole in my graph wherever that common factor, which was x, right? That was the common factor. Wherever that is equal to 0. Now, had that been, let's just say it was the x minus 4, like I had 2 of them, then I would set x minus 4 equal to 0. And I would have a hole at 4. But here, since it's just x, I set that equal to 0. And that's actually where I'm going to have a hole. Now, you'll see where that comes into play as I graph it. Let's just, for now, have it documented, okay? All right. Any questions on that? This is the function I'm going to work with the rest of the way, all right? This one right here. it's important that as we move on and get more information, that we don't go back to this one where we canceled, because we'll have some problems if we do. All right, so step D, find the x-intercepts. So to find the x-intercepts, what do we always do for a rational function? Set the numerator equal to 0. So we're going to take the numerator, which was just x minus 4, and set it equal to 0. You get x is 4. What is this on my graph? X equals 4.
It's an x-intercept.
It's an x-intercept. So is it, you know, if I draw it, what is it going to be? Just a point, right? Okay, that's going to be a point on my graph. Let's just remember that. This is a point on the x-axis. All right. Step E. What do we have? Find the vertical asymptotes. To do that, we set the denominator equal to 0. So you set the denominator. I called them VAs, right, instead of vertical asymptotes. Set the entire denominator equal to 0. And do I have to worry about the 2? No, I could divide both sides by 2 and it's gone, right? Don't make the mistake of saying that 2 is one of your answers, right? 2 does not equal 0. You can just divide it out. You get x minus 8 equals 0, and that's x is 8. What is this on my graph? Vertical dotted line that you cannot cross, right? Vertical dotted line. And we actually called it a barrier, didn't we? Because we are not allowed to cross it. We good? Okay. Now, let me point something out. You know how we canceled the x's earlier? If you went back to this version of the function and then went for the x-intercepts, you would set the top equal to 0, right? And wouldn't you get a solution of x equals 0? Wouldn't you say up here, not only is x equals 4 an x-intercept, you would have said x is 0, right? And then down here for the verticals, you would have set this equal to 0, and you would have also said that you have a vertical at 0, wouldn't you? And do you see the problem with that? You can't have an x-intercept at the same place you have a vertical asymptote. Because the x-intercept says you have to have a point, the vertical asymptote says you can't be there. And that's why canceling the factor is so important. That's where we have a hole. When you go to find your x-intercepts and verticals, you do not want to work with the original. You want to work with the one after you've canceled. Am I making sense?
Yes.
Okay. All right. So where are we? Step F. So this is where we have to determine the case. Well, yeah, it's case 3. Did I say 2 earlier?
Well, you said you didn't know.
Yeah, I hadn't looked at it. So for this one, we have to go back and take a look for the horizontal asymptote. We have to look at the original function and determine the degree of the top and bottom. I'm just going to write it the way it was given to us in the very beginning. Wasn't that it? Is that the original?
Yeah.
Yes? Okay. So when we look at this, for horizontal asymptotes, what are we looking at? What do we start with when we're looking at the horizontal asymptotes? The degree of numerator and denominator. So what is the degree of the numerator here? 2, right? So the degree of the numerator equals 2. What's the degree of the denominator? Is also 2, right? So you look at those, you compare them. Is it case 1? Is the numerator degree less than the denominator? No. Is it case 2? Is the numerator degree bigger than the denominator? No. Case 3 then, they're equal. And in that case, what does it say? Y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. So what's the leading coefficient of the numerator? 1. Do you remember how we did this a while back when we were doing that table and you had to find the degree and the leading coefficient to figure out if it was this, that, or that, right? It's the same sort of thing. You're looking at this number. It's a 1. So we put 1 here over the leading coefficient of the denominator, which in this case is 2. And that is your horizontal asymptote. And what is this on my graph? This is a horizontal dotted line, right? And we draw it where? At the ends only. Ends only. And how does it behave? Like, what does it do to our graph? What does this thing do to our graph? Do you all remember? Yeah, it draws it like closer to it. I said a magnet, you didn't like that. Right? Okay, you understand, right? I mean, you get the idea. So this is going to pull our graph towards it only at the end of the graph. So this kind of determines our left and right hand behavior of our function. Only the left, only the right. We good? Yes?
Okay, so after we cross out the common factors, then that's when we plug in is that when we plug in the test points for it too?
No, we're still not there yet. Oh, wait, for the test points.
Yeah.
You
Or
do,
we
you,
use the, or do we?
no, we'll use the one that we canceled.
Okay.
Yeah. All right, you ready? I think we're good. We're ready for the next step. We're ready to plot all the information. So we're going to start drawing a picture here. And always keep in mind that your final picture needs to look nice. So if you have to draw a picture first just to get an idea of what's going on, and then come back and do a final picture later, that's fine. You know, I've been doing this for so long that usually my first picture is usually going to be my last picture. Like, I usually don't have to draw it twice, but if you do, it's okay. I'd rather have it look nice and clean than a bunch of like mistakes that you crossed out. And understand? All right, so here we go. Here's my graph. I'm going to draw my x and y axes. All right. Here's x. Here's my function's value, which is the y. And I start with the first piece of information that I had, which was what? Before that, I have a hole, right? Remember that I have a hole at 0. Now, the thing is, I can't draw a hole yet because I don't know what the graph looks like. So the hole, you just have to remember, is here, all right, at 0. Just remember there's a question mark here. That's where my hole is. Yes?
Wouldn't you plug 0 into the whole original function to find the y-intercept?
But you can't, because the original function, if you plug 0 in, you get 0 on top and 0 on the bottom, and you get division by 0. So that's why that creates an issue. Does that make sense? All right, so now the x-intercepts. So where are my x-intercepts? 4, just one x-intercept? 4? So I'll go out, let's say 1, 2, 3, 4. Wow, I don't usually have a purple marker in the classroom. Interesting. All right, so that's part of my graph, right? Next thing, where is it? At 8. So I'll go out 5, 6, 7, 8. At 8, I draw what? Dotted vertical line. Barrier. It extends upward and downward forever. What was the next piece of information I had?
Horizontal asymptote,
Where was it?
y equals 1/2.
1/2. So let's say that this is 1 right here, right? 1/2 is up halfway. And what I need to do is draw a dotted line out at the edges only. So up a half, I come all the way out here, and I draw my magnetic dotted line. And out here, well, I don't really have much going on out here, so I'll just put it like this. Like that. You don't like that? Do you want me to go further out or something? Look, this right side, I drew it to the right of the last piece of information I have, right? The vertical is the last thing I know about this graph. So my dotted line just needs to be to the right of that. This dotted line for this horizontal just needs to be to the left of the last thing I know. And the last thing I know is that I have a hole over here. If I had another vertical over here, my dotted line would need to be out here somewhere. Okay. Is that all the information?
Yeah.
Yes? So now we get test points. So for your test points, do you remember me telling you how many you would have? One more than the x-intercepts plus the vertical asymptotes. We should have a total of 3 because we have one x-intercept and one vertical asymptote. So we should have a total of 3 test points. Yep. So someone give me 2. Okay, 2 is to the left of this x-intercept. Do you agree? So 2 I'm going to test. And then I heard, what, 6? 6 will work because it's between the x-intercept and the vertical. And then anything over here? 10? Why am I circling these?
Because you're only testing.
I'm just testing them. So I'm just letting you know those are the points I'm testing. I'm not putting dots at these points. So 2, 6, and 10. And where do you want to plug those in? To the factored and canceled, the most simple function that you have, which was f of x equals x minus 4 over 2 times x minus 8. That one right there. We're going to plug into that one. And I said there was kind of a short way of doing it, right? This is the short way. You're just going to look for signs. So let's start with 2. What happens when I plug 2 in? What do I get on the top? A negative. All right, on the bottom, I have 2 times this, right? 2 is always a positive number, isn't it? So really, this doesn't even really matter. But when I plug 2 in here, I get negative 6, which is a negative number. So you get a negative on the bottom, right? Does everyone see that 2 times a negative number is still going to be negative? Okay, so negative over negative? Positive. So I know that at 2, I need to do what? Just be above the x-axis. How far up? It's up to you. It does not matter, all right? Remember that we kind of wave our hands a little bit at this. We don't know how high and low these certain things go. So, I don't know, you tell me when. Okay, right there. All right, what about 6? What happens when you plug 6 in? What do you get on top? Positive on the bottom, negative, and a positive divided by a negative is negative. So that means when I go out to 6, I need to put a point below, right? So anywhere right here? Is that okay with you? And then when you plug in 10, what do you get? Positive. It's positive on top, positive on bottom, and so you get a positive number. So where do you want it? There? Okay. Ugh. This purple marker is almost dead. All right, now after you've done all your test points, this should be enough information to draw your graph. This should be enough. So let's draw it. And where did I say to start? On the left side, at the point that you know absolutely exists for sure on your graph, which is this one right here, right? There's nothing else to the left in terms of a point that you know of. And then we try and draw it to the left, and we draw it to the right with a nice continuous curve. So when I go to the left, what has to happen? It has to go to this flattened thing, right? This is going to pull it towards it. But as I proceed through, I heard it, I'm going to have what? A hole right there, right? And then it's going to flatten out towards this. Do you agree? How do I represent the hole? With a hole.
So the hole is on one.
It could be on one, it could be somewhere else. I don't know. Remember, the heights of these things we're not concerned about as much in this class. In a calculus class, you would actually try and figure out where these heights are occurring.
If x equals 0, that's still correct there?
What's that?
Even if x equals 0, it's still correct right there as far as the whole?
If you try and plug 0 into this graph, this hole says the graph does not exist there. Because the function, well, the original function, if you try and plug 0 into it, you get 0 divided by 0. So what we're saying is at 0, there's no graph. But we have to represent that somehow. If you just draw this straight through, then you're implying that the graph actually has a value there, and it doesn't. So we have to have a hole. Is everyone satisfied with the left side of that?
So it doesn't matter if it's on one or
That's right. It does not matter. I'm going to show you a different variation of this after I'm done. Another way someone could have drawn it, okay? And then from here to here is kindergarten, right? There's nothing in our way. Just connect the dots, and then you can kind of tell what's going to happen, but it's going to, the vertical barrier forces us either up or down. You can't go up, why? You don't have an x-intercept, and you would have to cross the x-axis, which is a no-no, so we have to go down like that. What about the right side? You jump over, you grab that point right there. To the left, it has to go up. And to the right, it's got to go towards this dotted line. And that's it. All right? Now, someone is going to come in and do something different with their test points and get something that looks a little different. So let me just show you. What if you had tested two and got your number and it was positive, but you decided to put it up here, right? And then let's say you tested 6 and you decide to put it here. And let's say you tested 10 and it was positive and you decide to put it here. How would your graph look compared to the green one? Well, to the left, it would have to go down towards the horizontal, right? And you would have a hole here. See, our holes are going to be in different places, though. And then to the right, it's kindergarten, right, like this, and then here. But you still are forced down, right? There's no way around that. You following? Over here, to the left, you're going to have to go up. To the right, you're going to have to flatten out. So the green graph and the red graph look very different, right? But they are exactly the same information in terms of what we found, right? They both get pulled down to 1/2 on the left. They both have a hole at 0. They're both above the x-axis here. They're both below the x-axis here. They both dive down on this side. They both go up on this side. They both taper off towards this, right? So we don't have any major differences in the graph other than the heights of points. All right? Does that kind of resolve your question? All right. I think this is a really good illustration. Let me erase this part. Let me just get rid of all the red stuff. I think this is a good problem to show you what would happen if you go to the tutoring lab to get help on this, or you have a friend who knows everything about math, and they tell you to draw your horizontal asymptote all the way across like that. That could be very confusing to most students because you'll get your test point here. You probably wouldn't put it there. You probably put it above or something like that. And then when you go this way, you might be like, okay, yeah, I've got a hole and I flatten out. And then here you might be like, wait a minute, hold on. What, you know, like that seems to be in your way. But it's not because it's a horizontal. It doesn't matter what's happening in here. It's the only. So that's just my warning to you, again, is don't confuse yourself by drawing that horizontal straight across. I've seen it happen many times. Okay, so let's see. That was a type where it gave us a case 3 when we got to horizontal, right? Now let's go and take a look at a problem where we're going to have case 2, I believe. Yeah, case 2. That one didn't take too long, like 20 minutes. All right, f of x equals negative x cubed plus 9x over x squared minus x minus 30. All right, we're going to go quicker through this one. Step A, it's a rational function. Step B is factor. The top factors, what can I pull out? Negative x. You're left with x squared minus 9. How about the bottom? Does it factor? Minus 6 plus 5, x minus 6, x plus 5. Is there anything else I can do? Top is difference of squares. There we go. Everyone okay with that factoring? We got a lot going on here, don't we? Got a lot going on. So what step am I on now? Step C. So what am I doing? X-intercepts or holes? What? Hold on. This was holes. Did we have any holes? No holes, right? No holes. No common factors. So that's good. We don't have to worry about that, right? No holes. So I can go to part C. If you need to write that down, go ahead. No holes. Little smiley face if that makes you happy. And then what? X-intercepts. So you set the top equal to 0. What are my answers? 0, negative 3, and 3. Those are points on my x-axis. I have 3 of them. Questions? Step D. Verticals, right? So set the denominator to 0. I got that backwards, sorry. This was plus. Minus here, plus here, so it gives us x is 6 and negative 5. There's no horizontal. Why? Okay, so is it all right if I write capital N and capital D to represent the degree of the top and bottom instead of writing degree of numerator, degree of denominator? So what's the degree of the numerator? Here's our original problem. 3. What's the degree of the denominator? 2. So when we look at our cases, this is case 2. The degree of the numerator is bigger than the denominator. And does anybody remember what I told you would happen in this case? I drew it over here. Remember? I said even though it's not on your notes, it's going to... Okay, good, yes. It's going to go up on the left or possibly down on the left. And then it's going to go up on the right or possibly down on the right. And we don't know. What we do know is that it doesn't flatten out. And if it doesn't flatten out, it's got to go up forever, it's got to go down forever. So we'll be able to determine that pretty easily once we get our test points. Okay? So that's what we have. No horizontal. This is case 2. No horizontal asymptotes. So we're ready to put all the information down, right? Draw a picture. I'll draw my picture a little smaller over here. Okay, here it is. I've got a lot going on this picture. X-intercepts at 0, negative 3, and 3. Those are points on my graph. That. I have 2 vertical asymptotes, one at 6 and one at negative 5. I have no horizontal asymptote, so I'm not going to draw anything. I'm just going to remember how it's supposed to behave. How many test points are you going to have? 6 of them. I realize that sucks, but, you know, could be worse, right? Could be 8. Could be 6.5. So what test points would you like here? Okay, I saw -4, that's correct, but you need something a little further to the left of that. -6, -2, 2, 4, 7. That good? We have one in between each vertical and each x-intercept, and on each end we have something. And we have the pleasure of plugging that into this. -x, x plus 3 times x minus 3 over x minus 6 times x plus 5. And we're going to plug in -6. We're going to plug in -4. We're going to plug in -3. We're going to plug in, no, sorry, -2. 2, we're going to plug in 2. We're going to plug in 4. And we're going to plug in 7. Any questions on the test points? Okay. All right, be careful here. When you plug in -6, what's this top left? +6, right? -6 is +6. So I have positive on the top left corner. -6 in here. -6 right here. -6 minus 3. -9. Careful because you're subtracting, not multiplying. What's -6 minus 6? -12, and then -6 plus 5. -1.
So it's an 8.
Positive on top, right? Because these two together are positive, and you put the two positives together, you get positive. Negative times negative is positive. Positive over positive is positive. Yeah? No? Yeah? No? Yeah? So I'm going to come over here to -6, and I'm going to put a dot where? Anywhere I want, above the x-axis. Okay. So up here, and then you go through the process, right, and you continue this. Does anyone think they're going to have any issues plugging in those values? I'm not going to take the time to do it, but you know what you need to do here? For this particular problem, it's going to alternate every single time. But it will not do that guaranteed every time on every problem. So you have to check them. So this one should turn out to be negative. The next one should be positive. The next one will be negative. The next one will be positive. And the last one will be negative. Check for yourself. Okay. So you get over here at -4, I need to put a point anywhere below, right? At -2, I've got to put a point above. At 2 below. At 4 above. And at 7 below. And that should be enough for us to draw the picture. Do we have any questions on this? Start at my leftmost point. All right, I'm going to call on y'all this time. I'm going to just go around and see how y'all are doing with this. We'll start over here. David, right? David, this point right here, what should I draw to the left? Should it flatten out to anything?
No.
Okay, and we said earlier if it doesn't flatten out, it's got to do what? Up or down, right? It's either got to do this or it's got to do this. Now, David, can it do this? Why not? That's right. It would cross the x-axis, and we don't have one there. So it's got to go up, right? So it's going to curl up like that. Jordan? You're next. Drawing out to the right, Jordan, what am I going to do?
Or to the right.
If I draw this to the right, what has to happen here? Can I cross through the dotted one?
It would have to go up.
It would have to go up. Why couldn't it come down, though?
You can't just say
because it can't touch the x. And I can't cross that, so it's going to have to turn back up like this. That's it. It almost looks like a little U over there. Thing is, this side goes up forever, this side goes up forever, but it goes out and up forever. It's a little different. Good. Okay. Lily, right? Lily's next. Okay, Lily. Where's our next left point, or our next closest point? Where is it? At -4 down here? Okay. You have to draw it to the left and to the right. So what do you want me to do to the left? Go down. So dotted line is going to force you down. Lily, why couldn't I do this? Lily? You're not Lily, are you? Did I get y'all? I didn't get y'all mixed up today, did I?
No.
Okay. You can't turn back on yourself like this because it would fail the vertical line test. It would fail to be a function. I just don't want y'all doing anything crazy like that and not realizing why you can't. This was correct. We dive down to the left. Can't go up, right? Because you can't cross the x-axis. See, that's what I was afraid you would say. Yeah, I can turn up and come back. But then that would, everyone understand? If you did that, it would loop back and you would fail the vertical line test. Okay. All right, we'll move on. What do you want me to do to the right here?
Go up towards -3.
Okay. And then what?
Keep going.
Up to this one?
Yep.
Once I get there, what do you want me to do?
Start coming back down.
Okay. So we're in kindergarten now? Okay. Here,
Yes.
here,
Keep going.
here.
Yep.
Uh-oh.
You go down.
What do I do here? You can just continue to go up, right? Pull up forever, like that. Doesn't that middle piece almost look like a polynomial function? Like the ones we did before this? The difference is that it's stuck between two vertical lines. Like a real polynomial goes out and down forever. This one goes, out and up forever. This one's stuck between two vertical walls. Okay, who's up? Giovanna.
Okay.
You get this last point here.
Okay, so it's gonna go down.
To the left, down?
Yes.
Okay. And what about to the right?
Also down.
You want me to curl back like this?
Yeah.
And that's because out this way, it had to go up or down. Couldn't go up. Why?
Because it will hit the.
It would hit the x-axis, so it has to curl back down. That's it. That's the graph. Make sense? Okay, the next thing I'd like to do is a word problem. And then after that, I'm going to give you one more of these to look at. But we need to do a word problem. Well, no. I don't think like is a strong enough word. No, word problems are the ones that make most sense because there's no sense in you having math if there's nothing you can do with it, right? All right, I'm going to copy this straight out of the book. I'm in version 9 of the book, but I'm going to write the whole problem down, so. All right. You ready? This is a lot of words I'm about to put up here, all right? The title of this problem is minimum cost. Minimum cost is the title of this problem. A rectangular area adjacent to a river is to be fenced in. No fence is needed along the river. The enclosure must be 1,000 square feet. Fence along the side parallel, there's a lot of words in here, to the river is $10 per linear foot. Fence perpendicular, I'll just write perp, is that okay? To the river is $14 per linear foot. The 4 corner posts are $28 each. We're almost done.
I feel bad for you because you're about to erase it all.
I am. Find and sketch the cost function for this project. And that's it. So this is more real world. I mean, you might still argue like, yeah, right, like you'd ever need to do this, but more importantly is how you construct a function from a real, like, physical problem. So let's see if we can turn all these words into a picture, right? You've got a rectangular area. So rectangular, everyone knows what a rectangle is, right? It's going to be next to a river, right? It's going to be next to a river. We need to build it so that it has 1,000 square feet, so it can hold 1,000 square feet. We need to do it in a way where we keep in mind that the cost of the fencing parallel to the river is $10 per linear foot. The cost for the fence perpendicular to the river is $14 per linear foot, and then the corner posts are $28 each, and we need to figure out cost, right? So, time to draw picture.
Does that seem a little bit unrealistic?
No, not at all. No, it doesn't.
Was never there.
All right, so I'm going to start off with a river. Now, we are assuming that this is a perfectly straight river. And we're looking from the top, okay? That's my river. And that's the water. And it's flowing in that direction, even though it doesn't matter at all in the problem, right? So there's my river flowing. And I need to build a rectangular enclosure along this river. So that means I need to build it like this, and like this, right? And it said I do not need to build a fence along the river, right? That's what it said? I don't need a fence along the river. Does everyone agree that that's one way I could do it? Yes? Do what way?
Like, you could have the river at the top or at the bottom and just have the box going the other way.
Oh yeah, like I could have moved this picture, yes. But what I'm trying to get at is, could I have done this instead? Yes, right? Didn't specify, it just needs to be a rectangle and 1,000 square feet. So let me see, would this work? I'm just throwing some numbers in here just for the sake of doing it. Would that work? Would that give me 1,000 square feet? Yes? We're done. Okay, would this work? Yes. So let's call this, this is just brainstorming thinking right now, okay? Let's call this rectangle A, or no, let's be more mathematical, okay? Let's call this rectangle 1 and rectangle 2, all right? R1 and R2. What is the cost of building R1? What is the cost of R1? How does that look to you? Does that look like a math person's way of saying that? What is the cost of building rectangle 1? So what is the cost?
Well, you know, 48 times 4.
Okay, so you want to talk about the corner post first? I'm going to need corner posts in all your corners, right? You're going to have that, right? Going to have to? So those are my constants. So 28 times 4, was it $28? Was it? What's 28 times 4? 28 times 4. Let's just write it like that. We'll write the actual number on the next line. 112. But we'll do it on the next line. Does everyone understand this is the cost of the posts, and this is how many of them I need? Yes?
Yes.
All right. Now, on top of that, I've got to pay for the fence that runs parallel to the river, parallel is this way, and the fence that runs perpendicular to the river. Now, don't ask me why those fences cost a different amount. I don't know. They gave us the problem, all right? So how much does it cost per linear foot for the fence parallel to the river? It was $10 per linear foot. So I'm going to have to pay $100 or 100 linear feet times $10. Agreed? Plus, how about the fence that is perpendicular? How much does that cost? Is it $14? Yes? Was it 10 or was it 12? I thought it was 10. Okay, so perpendicular was 14? Yes? Okay, so, but I have how much linear footage do I have here? 20, don't I? I have to build that one, which is 10, and this one, which is 10. So that's going to be 20 times 14. Okay, so this is the cost of the posts. This is the cost parallel fence, right? And this is the cost of the perpendicular fence. Are there any other costs that I'm missing here? No, this is it? Everyone see it? How much is this? So it's 112 plus 1,000 plus 280, which is 1392. So $1,392 is how much it would cost me to build it this way, right? Is the cost going to be the same if I build it this way? No? Well, let's see. The cost of building rectangle 2 will be the 28 times 4. That shouldn't change, should it? All right, and then I have, how about the parallel part? It's only 10 feet, right? The parallel part is only 10 feet at $10 a piece, or $10 a linear foot. Plus, how much? Yeah, we have 200 that's perpendicular. It's 100 here and 100 here, so you have to build 200 feet at $14. I think this can be more expensive. What does that cost come out to? Anyone do it yet?
3,012.
3,012?
Yes.
3012.
Yes.
Okay. That's the cost of doing it that way. That's right, that's tax.
Yeah, times 0.08 on that. Well, 0.085.
Now, the reason that this is a good problem is because this is more applicable to real world stuff. You know, if you're a company and you're building all these pens, right? Let's say for chickens, and you know, you're designing the chicken coop for Tyson. Tyson, don't they make chicken? Tyson chicken, whatever, and you're designing the coops, but they have a water source. The chickens won't go out into the water because they know they'll drown, so they just build them this way. And you could just go and just be like, well, look, each chicken needs a certain amount of area, and just build them however you want. Or you can actually think about it, because if you just build it however you want, you could pick this way and it would be better than this way, right? But you could also just randomly pick this way and be like, oh wow, I just spent almost more than twice the amount of money I needed to. Yes?
So you could do it either way.
That's right.
Problem.
Oh no, but what we want is the cost function. All this is doing is getting you to realize and understand that the way you build the fence matters, doesn't it? It does matter. It changes the cost. What we want to ask, the ultimate question that we want to ask in calculus is, how do I build it to have the minimum cost? Right? We can't answer that question in this class. But in Cal 1, you start with that. So in Cal 1, you do a bunch of stuff to figure out ways of finding the lowest and highest points on graphs. And then they all of a sudden throw a word problem at you like this. And you're like, what? So that's why in this class, we at least get you exposed to a word problem like this, so that when you're in Cal 1, you're like, okay, I've seen that. We've built cost functions before. Now we can actually answer them. We will answer this question today, because I'm going to graph it and we're going to find the minimum value. But we won't be able to do it ourselves. What we want is just the function first. Okay, so are you ready to build ready to build a 1,000 square foot pen, but not fix any of these sides? You ready to do that? Okay, good. You don't have a choice. Here we go. Why what?
Why are we building this fence?
For the chickens, I guess. I don't know.
For Mike Tyson's chickens?
For Mike Tyson's chickens, yes. All right, so I'm gonna go like this, right? And instead of me actually using a number like 10, I'm just gonna call this side X. And then this one, you wanna call it Y? Okay, what can you tell me about X and Y? What's the relationship between X and Y?
Square footage.
What about the square footage? It has to be 1,000. So does everyone agree that we know that X times Y must be 1,000? Does everyone agree with that?
Yes.
Yes? All right. Now, let's get the cost of building this thing. The cost of building this will be, well, is there any way we can get around the four corners? No, we got to have the four corners, so 28 times 4. Well, we know that that's what, 112? I'll leave it as that, though. Okay, plus,
2x.
did we do the parallel first on the last one?
Yeah.
Let's do the parallel first, then we'll do the perpendicular. So how much fencing is going to be parallel to the river? How long is this? Y, right? It's Y? And how much is it? $10 per linear foot. So this should be 10Y. Yes? 10Y. Plus $20, or was it 20? 14? $14 times this side and this side. So how long is these two together? 2x? So I'm going to put it this way. It's $14 times the length, which we said is 2x. So I'm hoping you're seeing here, this is still post, this is still the parallel part, this is still the perpendicular part. Is everyone following me?
Is there going to be a problem if we just make that at 28x?
Oh yeah, we're going to make it 28x right now. I just want to make sure we all understand where every piece is coming from. $28 per post, 4 posts. $10 per linear foot parallel to the river. This is how long the part parallel to the river is. $14 per linear foot times the length of this stuff perpendicular. It's 2 times x. All right, clean it up. The cost function is 112 plus 10y plus 28x. We want this to be a cost function, though. This is a cost equation, but it's not a function. To have a function, we need to be able to determine cost in terms of a single variable. Notice that we have 2 variables in here. In order for me to tell you the cost, I have to tell you what x is and y is, right? So we're trying to get it to turn into something that we can graph. Do y'all see what I'm saying? Like, you can't graph this because how many things don't you know? You don't know x, you don't know y, you don't know c. Everything we've always graphed, we've had just one variable in it, right? Just x. So I'm now going to come back here and try and turn this to a cost function. And the y is the thing giving me the trouble, isn't it? What have I not used in this problem so far, though? What is the one piece of information I have not used? I wrote it down, but I didn't use it yet.
We know it's 1,000.
I know that it's 1,000, right? So can't I take this equation and solve it for y? If I solve that for y, you get y is equal to 1,000 over x, don't you? So now we write down 10, and then instead of y, we write 1,000 over x, then plus 28x. Questions? So what is this cost function? Because I can call it a function now, can't I? This cost function is 112 plus, how do you multiply this? What happens here? Isn't this like 10 over 1 times that? So you just go straight across? 10,000 over x? Plus 28x. Are y'all all right with this? Okay. That is the cost function. That is it right there. Now, what is difficult for you to see right now is that is actually a rational function. So let me show you why this is a rational function. I would like to get a common denominator. Isn't that how you put fractions together? You get a common denominator, right? So if I look at these all as fractions, this over 1, this over 1, what would my common denominator be? X. So I would have to multiply the top and bottom of this one by x, top and bottom, right? I have to multiply the top and bottom of this one by what? X also. What would you get if you did that to get your common denominator? You would have 112x over x plus 10,000 over x plus what? 28x squared over x. They all have the same denominator now, don't they? Don't they? Yes? Okay, so I can put these all together into one fraction? Thank you. And so when I put them together, it's 112x plus 10,000x plus 28x squared. I'm going to rewrite that in descending order on top. All over x. I just changed the order of things. What type of function is this? It's a rational function. It's a polynomial divided by a polynomial. Do we know how to graph that? We should. Let's do it now. Okay? Let's graph it. So I'm going to go through the process. Step A. Is it a rational function? Yes. Step B. Factor the top and bottom. Uh-oh. Uh-oh. I can take a 2 out. Can you take anything more than a 2? Does a 4 come out? 4 does? Anything more? Does I think a 4 is probably the biggest thing we can get out of there. Unless 28 comes out. Does 28? All of them? No, 28 comes out of the first one. I don't think 28 is going to work. Doesn't come out of the last one? Okay, so I'm going to show you something here that will be very useful